Hello everyone. From now on, I decided to put my lectures on video. I'm going to be uploading on Blackboard. You'll be watching a video before each lecture, take a pre-lecture quiz, and come to class prepared. The reason I decided to do that is that in the class, we did not have enough time to do learning activities and learning catalytics or solving extra questions to help you learn better. So my aim again is to teach you better. I hope it will be helpful. From now on, before each lecture, I'll be uploading lecture videos about 30-45 minutes length with the examples and everything. As if I'm in the classroom, I'm going to be explaining you everything. Please watch these videos, write down your questions while watching, or post your questions on my Twitter account I've given to you. Once I come to the classroom, first thing I'm going to do is to answer your questions, give some more examples if I want to give, some demonstrations if I want to do, and then we'll move on to solving questions on learning catalytics. This way we'll have longer time to work on learning catalytics and learn better, solve more questions, hopefully, and I hope you will like it too. So today I'm going to be giving you the lecture, pre-lecture lecture for Monday, next week's Monday, and it will be about Newton's laws. This section is covered in your book as Newtonian Mechanics, Chapter 2. So let me put Chapter 2, Newtonian Mechanics. And I hope you can see this fine. So first of all, in Newtonian Mechanics, we deal with the forces, how forces are acting on objects, and how large acceleration they are given to the objects. Total forces, which direction the object moves, and what's the acceleration, stuff like that. And we're going to start with Newton's laws. Very important. So Newton's laws, very famous topic of physics. I'm sure you've heard of here, there, or you already know what they are. So we're going to discuss them. First law. Newton's first law is also called the law of inertia. Law of inertia simply is the tendency of the objects, any objects in the world, to keep the state of their state as long as they can. So if an object is in stationary state, it wants to stay in stationary state forever. If an object is moving with a velocity, it wants to move with the same velocity, constant velocity forever, unless a force is acting on it. This is simply what a law of inertia is. Let me read it to you from here for better English. An object continues in a state of rest or in a state of motion at a constant velocity unless compelled to change its state by a net force. This is the first law of Newton's motion. And I put a post on Twitter and asking you to post examples from life that proves that Newton's laws actually holds. And I'm going to give you one example here. When we get on bus, for example, or in our car, first we're stationary sitting, we are objects and we want to stay in the same state. So as the car starts to accelerate and move, we're pushed back because our body wants to stay in its stationary state due to the law of inertia. That's why we're pushed back. The same thing happens when we hit the brake and we start slowing down. We're pushed ahead because now we're used to moving. We still want to move, and we are pushed ahead because of that law of inertia. Give me some examples from life for bonus marks on Twitter. So this is law of inertia. Newton's second law is maybe the most important law that we will be using as an equation and in our questions in this section. Newton's second law is simply stating that when a force is acting on an object, the object gains an acceleration which is inversely proportional to its mass. What this also tells me is that if I exert the same force on two objects, one is heavier or more massier than the other, the massier one will have a smaller acceleration. So acceleration is inversely proportional to the mass. That's what simply Newton's second law states. And let me give it to you here from my notes, again, for a better English. I'm going to post these notes online in Blackboard at the end of the lectures when all topics are covered, so you'll have them as well. But it's better if you write down your own notes. So Newton's second law states that for a given net force or total force, the magnitude of the acceleration is inversely proportional to the mass. So what this tells me, if I apply a force F to an object which has a mass m, let's see, I'm pulling it. This object, first object I applied, will gain an acceleration a1. And if I apply the same force to another object, let me call this also m1. With a larger mass, let's call m2, apply the same force, F, the second object will gain an acceleration a2. Since m2 is larger than m1, this tells me, through Newton's second law, a2 is smaller than a1. And this gives me the equation, actually, for Newton's second law. The force acted on an object, F, vector, don't forget, we'll be dealing with them as vectors, is equal to mass of the object times the acceleration. This is simply the summary of Newton's second law. If we apply a force to an object, the force will give the object an acceleration which is inversely proportional to the mass of the object. Force is a vector, acceleration is a vector, and the acceleration direction is always in the same direction as the total force. Over here we have only one force, so if my force is to the right, I choose it in my positive direction, and acceleration will also be positive. In this section of our course, we will be choosing the direction, positive direction, always with the same direction of the total net force acting on an object. What I mean by total net force, if there's more than one force is acting on an object, let me put it in here, if there are more than one force, one force acting on an object, and we look at the total force. We add up all these forces, keeping in mind that they are vectors. Directions are also important. Let's say I have an object, let me put this as an example, with mass m, and I have two forces acting on it. One is pulling, F1, the other is pushing. Let's say with the red one, let me draw this, F2. Now my total force or net force is called both interchangeably. My F total is showed like this sometimes, or total F, I'm showing my vector because I'm going to be doing vector addition, is equal to F1 plus F2. Vectorial addition. And still this F1 plus F2 is equal to n times A. This never changes. So if I have more than one forces, I'll be looking at total force, and the total force is equal to m times A. These two forces are pushing in the same direction. They will be given this object an acceleration in the same direction as well. Total force is to the right. For this question, my positive direction will be to the right. And we will always, again, going to be choosing the positive direction to be the direction of motion, which is the same as the direction of total net force. Now, forces may not always be in the same direction, may not always be along horizontal. These are all important because we are dealing with vectors. So Newton's first law, law of inertia. If an object is stationary, it wants to stay stationary. If an object is moving, it wants to move forever, unless a force is acting on it. Second law is if a force is exerted on a mass, The force gives the mass and acceleration which is inversely proportional to the mass and directly proportional to the force exerted on the object. Now I'm going to delete this and give you Newton's third law. I also forgot to tell you that I couldn't give you pre-lecture quizzes always because your book, online book, did not have something helpful for you to understand before coming to lecture. Those videos, they had them only covering some part of the topics. From now on, since I will be putting my lectures online, you'll be watching before lecture and take pre-lecture quizzes. Before each lecture, you're going to have some one pre-lecture quiz with some questions, 4 or 5 questions again. Hopefully. So keep up with this. Hopefully you'll be able to keep up with this as well. So Newton's third law. Newton's third law states that if there is a force acting on an object by another object, by a second object, the first object exerts the same force in opposite direction to the second object. So if I am hitting my hand on this table, my hand hurts because the table is hitting me back with the same force, equal magnitude, opposite direction. The harder I hit, the more my hand will hurt because of the exerted force on my table, on my hand by the table. If I hit on the board, the same happens. So if there is an object and I'm exerting a force on an object, let's say I have mass in here, and I'm pushing the mass down with the force. So I'm pushing on the floor will be pushing back. With a force that is equal in magnitude to the force I was pushing and opposite in direction. Let me put this F in here. And these forces are often called action-reaction forces. The force I am pushing with is my action force. I am the acting object, and the floor pushes me back with the reaction force. Let me also read this to you for better English. Newton's third law. Whenever an object exerts a force on a second object, the second object exerts an oppositely directed force of equal magnitude on the first object. And the third law is often called action-reaction law as well. So these are Newton's 3 laws of motions. Give me some examples from live on Twitter for bonus marks. And please use hashtag for me to find them easily. Our hashtag is physics 1410. Bonus for only bonus marks. And for any questions, just say physics 1410 hashtag. And if you want to put some comments about the labs, please use hashtag physics 1410 labs for me to find them easily and try to answer your questions or take your recommendations, comments into account. Okay, so we are done with Newton's laws. Let me now give you some examples. Again, the law of inertia, force is directly proportional to the acceleration, and mass is inversely proportional to the acceleration, and action-reaction law, to summarize. And the one we're going to be mostly dealing with will be the second law. Let's solve a question involving the second law. I'm going to delete this now again. I'm really hoping that you can see the board. Okay, my light is kind of very good in here. And I'm also hoping that you can hear me. Okay, Newton's law example. You may write down these examples or just watch this video over an hour or two. Understand these well and take the test, pre-lecture test. Okay. So we have a diagram in here. We have a spaceship. Okay, I hope I can draw this good. Kind of a spaceship I'm drawing here. I don't know, this is what I have in the picture. And we have an astronaut pushing the spaceship. So astronaut in here with his hand pushing the spaceship. So as the astronaut pushes the spaceship, we have force F, right, vector. Due to the third law, Newton's third law, action-reaction, the spaceship will be pushing the astronaut back. And from general intuition, we can feel that. Whenever we push something, it pushes us back, and we always feel that. If you push someone, you're also pushed back by that someone you're pushing. So the spaceship will be acting on the astronaut with an equal force, equal in magnitude, opposite direction force. Now let me read you the question. Suppose an astronaut exerts a force on 36 Newton, force of 36 Newton. So the force of the astronaut is 36 Newton. Can you see that? Let me put this with black. So the astronaut is pushing with 36 Newton to the right, and the force pushing the astronaut, reaction force, will be also 36 Newton, only in opposite direction. Find the acceleration of the astronaut and the spacecraft if their masses are, so the mass of spacecraft, I'm going to call it ms. If their masses are 11,000 kilogram, so this is the spaceship, and I'm going to call the mass of the astronaut 92 kilograms. Now we have the same force, yes, only in opposite direction. As the astronaut pushes this spaceship to move a little bit to the right, he will be pushed back, so he will be moving to the left. We can choose directions here, but we don't have to actually. All we need to find is their accelerations. But if we want to define direction, let's choose the direction of the spaceship positive, and the direction of the astronaut will be negative. But we don't need to, for this question, we'll find only the acceleration for both. So let's find for astronauts first. So acceleration for the astronauts. Just checking time to see how much time has passed. What am I going to use? Total force. Let me put this. We have one force, but I'll put this to help us understand better. Is equal to m times a. I'm going to call the a astronaut, maybe AS. It won't be AA. Confusing. So F is equal to ma. What is the force acting on the astronaut? To the left, yes. And the value is 36 Newton, equal to the action force. So 36 Newton as well. So I put this in here. 36 Newton is equal to mass of the astronaut. Let me put here ma as well. Well, let me make this an astronaut, so it will be more definite. An astronaut 92 kilogram time a astronaut, I don't know. This is vector, but I am interested in its magnitude. It's towards left, I know. And I'm just gonna find the magnitude. From here, a astronaut is equal to 36 Newton divided by 92 kilograms. Over here I might stop. I forgot to tell you something. When we were finding force is equal to m times a is our acceleration, and we know its MKS unit will be meters per second squared. M is our mass, kilogram. And for the force, we'll have meters per second squared times kilogram. Let me put this in here. Kilogram meters per second squared, MKS units. And this is called Newton, and the name of the founder of this equation and law, Newton's law. So this Newton is the unit of force, and it's actually kilogram meters per second squared. When I divide it by kilogram, I will get the unit for acceleration, meters per second squared. From here, for the astronaut, what I have, and please check my answer again, acceleration is 0.39 meters per second squared. For the spaceship, we do the same. MS, FS, let's say, F spaceship, total F spaceship, is equal to M spaceship times A spaceship, AS times MS. Total force is acting to the right, positive, but I'm just taking magnitude now, 36 Newton. And the mass of the spaceship is 11,000 kilograms. 11,000, yes, kilograms. Times the acceleration. Again, I'm looking at magnitude, so I'm deleting the, I found the direction already, so I'm deleting the vector sign. And a spaceship will be 36 Newton again, divided by 11,000 kilogram will be equal to 0.0033 meters per second squared. Please check the answer to see if it's correct. F is equal to ma. If there's one force only, my total force is one force, easy. If there are more than one forces, we'll have to add up these forces, taking into account the direction because they are vectors. If you have any questions, keep it in mind. Write it down, email me, or post it on Twitter. Now let me give you an example, a simple example, where we have more than one force. In different directions. So this is yet another example. Let's say I have a mass M. My mass is equal to 5 kilogram. And one of the forces I have is pulling this mass to the right. F1 is equal to 20 Newton. And another force is pulling it to the left. F2 is equal to 40 Newton. Now in these questions, sometimes question defines the directions, then we'll take the directions into account, but what we will use generally is the direction of motion and the direction of total force to be the positive direction for us. If I look at this question, I have two vectors in opposite directions. I can guess that it will be moving in the larger force direction. So I'm choosing my direction to the left to be positive, to the right to be negative. And we will be always doing this in this section, Newton's laws of Newtonian mechanics. So, what is the acceleration of the object? A is equal to question mark. First of all, my direction of motion will be in the larger forces direction. So the acceleration will be in the same direction. I've defined my directions now, positive, negative. Now I'm going into the equation. Total force, F, vectorial addition is equal to M times A. And total force will be Let me put it in first in vector form. F1 plus F2. This is in vector form. I didn't move into magnitude form yet. Once I move into magnitude form, here I'll have to take positive, negative into account. I'm doing vectorial addition. This force is in positive direction of my choice. You can change your choice. It doesn't matter. Result will be the same. But we'll be always choosing the direction of motion to be positive. So we'll be consistent. And the F1 is in negative direction. So when I'm putting the magnitude of F1, it will be negative. Minus 20 Newton plus 40 Newton is equal to M, 5 kilograms, times A. Now I moved in the magnitude mode. I dealt with the vector section. I decided which one is positive, which one is negative. Now I can deal with the numbers. And from here, I'll get 20 Newton will be my total force. So F total here, or F net, also called total F, is in left, towards left, positive direction, 20 Newton. And A is in the same direction. So I'll get a positive value for A, which is why I have always chosen the largest direction of motion to be positive, to ease my work and always be consistent with one choice. If you're comfortable with changing this, go ahead and do it. It's perfectly doable. It's all optional. 20 Newton is equal to 5 kilograms times A, so 20 over 5. 20 Newton over 5 kilogram is equal to my A magnitude. A is equal to 4 meters per second squared. When I divide near my kilogram, I get meters per second squared. Because again, Newton is equal to kilogram times meters per second squared. If I divide this by kilogram, unit works as if numbers, so kilograms cancels, I'm left with meters per second squared. So here's it. So we'll be going into more complicated solutions and questions in the part where we see applying Newton's laws, the third chapter of your book. But this is so far what we need to know. I will also give you one more example of a little bit more complicated situation. So I'm deleting this. I hope you wrote it down, or you want to watch this video again if you forget what we were doing. I'm going to give you another example which is slightly more complicated. What if I exert a force on two masses together? Then I'll be looking at total mass when I'm applying my Newton's second law. So this example is dealing with that situation. We have here M1 and M2. Oh, which one is larger? Let me change here. M1 is larger. Okay. Alright, I'll redraw this. M1 is larger, so we make it consistent. M1, M2, two masses are touching each other, and we're pushing these masses with a force F vector. This system will be moving to the right. It's obvious. Assume friction is 0. So there is no friction. We'll get to friction later. Or air drag. Air drag. So motion is to the right. For this, my positive direction is to the right. And let me see the question. A, find the total acceleration of the system. Let me see what the force was here. Suppose a force of 20 Newton is exerted on the masses M1, 15 kilogram. So F here is equal to 20 Newton. M1 is equal to 15 kilogram. And M2, 5 kilogram. So supportive forces are exerted on two masses with M1 15 kilogram, M2 5 kilogram. A, what is the total acceleration of the system. So A total is equal to question mark. I can also call this A. If a system of masses are pushed with the force, they are moving together, their acceleration will be the same. So for this system, for M1 and M2, even if I have M3, M4 up to M10, they are all pushed together, they all have the same acceleration. But for the system, I will have only one A total. And from now on, I'll call it A for simplicity because they will be always equal to each other if they are moving together. To find the total acceleration, I'll look at total force. I write down my Newton's second law. F total now, vectorial addition, is equal to M total. M is a scalar quantity, so I'll be just adding them simply to each other, times A total. And from now on, again, I'll call A total A because the system will always have the same velocity, acceleration, sorry. So M total times A. Now moving into the magnitude formula, I know the magnitude of force. I have only one force, so my total force is only 20 Newton to the right. So I put this direction to be positive. 20 Newton is equal to M1 plus M2 times A. From here I can get my A. I know M1 plus M2. M1 is 15 kilogram, M2 is 5 kilogram. So 20 Newton is equal to 15 kilogram plus 5 kilogram times A. This is also 20. So A is equal to 20 Newton over 20 kilogram. Kilogram, 1 meters per second squared. So this whole system has 1 meters per second squared acceleration. Accelerates towards right, positive direction of my choice. So A is equal to 1 meters per second squared to the right. This is A. So if I have more than one masses, I add them up. Scalar addition, scalar quantity. If I have more than one force, I add them up. So the general form of Newton's second law is F total is equal to M total times A total. And A total will be the same for all the masses or objects that are moving together. So this is A. What is the acceleration of the system? Now I'm going to delete this and ask you B. So we got A now, 1 meters per second squared. B is asking me to find the force exerted on M2 by M1. Now, B. Force exerted on M2 by M1. What is this force? To do this, what we do is separate these two objects. They're not separate, but to consider this, we can do this. Separate them and consider only M2. We'll get to M1 later. So let's say there is a force exerted on M2 by M1, and let's call this F2. So M2 has a force exerted on M2, exerted on itself by M1, and we call this F2. Okay? Let me delete this M1 now. Just leave with M2. Now the system had an acceleration. I know that A total, which I called A, and I know it's 1 meters per second squared. And this is also equal to A1. All the objects in the same system accelerated with the same acceleration. This was my direction of choice for the system, so I'm not changing it. I don't want to change my direction in a question, otherwise I would get a wrong answer. That's important. If I pick my direction, I stick with it, always, for all the parts of the question I'm dealing with. Now, I have an object. I have a force exerted on it. I don't know the value. And this force is exerted on M2 by M1. I know that, but I just don't know its value. And it should be to this side, to the right, because this object is moving to the right. I know that from this whole system. Can I find F2? Yes, I can. I can apply Newton's law only on M2 to get F2. So F2 will be equal to M2 times, okay, why did I call this A1? This should be A2, of course. Sorry about that. So A2, same thing, only the notification was different. So F2 will be M2 times A2. Do I know M2? 5 kilogram. Do I know A2 is equal to a total 1 meters per second squared, so I can get F2. F2 is equal to 5 kilogram times 1 meters per second squared is equal to 5 Newton. Okay, so I separated M2 and solved Newton's law. Newton's law still holds for M2 alone. What is different is the force exerted on it by M1 is different, and I got it by using the fact that the system has the same acceleration. Okay, this is part B. Part C says, I'm going to delete this now. Let me delete it all. So right. And part 2 says, what is the force exerted on M1 by M2? Now, we are moving on to M1. So C, force exerted on M1, changing this by M2. And this will be found using action-reaction. Okay, so we have these two masses. We are separating them to see this. We found the force exerted on M2 by M1, F2, is equal to 5 Newton to the right, and it's my positive direction. Due to action-reaction forces, if M1 is acting on M2 with a force that is equal to 5 Newton, the M2 will be reacting back on M1 with a force that is equal to F2, opposite in direction. So I will have here F1, force exerted on M1 by M2, is equal to minus F2, and this will always be the case. This is magnitude, equal in magnitude, opposite in directions. Okay, so if F2 was 5 Newton, F1 is also 5 Newton. I have directly found it. Is this the only force acting on M1 though? No, the initial force F is also acting on M1. So if I am dealing with M1 separately, the total force acting on M1 is F minus F1 or minus F2, because it's an opposite direction, so the direction of F1 is negative. F and F2 are positive. This is important, and I can find whatever I need to find. A1 is also equal to A is equal to 1 meters per second squared. So go ahead and practice. Recover the fact that if you have M1 only here alone, this is just for you to practice. Assume you don't know A1, it should be 1, but assume you don't know it. You only know the forces F, 20 Newton, and F1, 5 Newton, negative direction. Don't forget your initial choice. And find A. Recover 1 meters per second squared. This will be a good practice for you. And M1 is equal to 15 kilograms. Ask me any questions you have so far about Newton's laws and first initial applications of them, and go ahead and do your pre-lecture quiz before Monday. Come into the class. See you.